Welcome to today's video in Mathematics 1. Today we're going to introduce one of the most important topics in that, maybe in the next semester. We're going to talk about equations. More precisely, we're going to talk one equation, but systems of equations, systems of so-called linear equations. Again, this is a topic that some of you will probably be familiar with from school. However, in this and in the videos to come, we'll develop a more systematic approach to this topic to get some insight into the structure of these systems and in particular their solution spaces. However, before we do so, I'd like to present you a brief application that highlights some of the most important points of that topic already. And then we'll go into the detail, see how we can solve systems of linear equations, how we can write them down in an efficient way, how we can characterize the solution spaces, and many, many more topics. So this introduces the chapter that is called Systems of Linear Equations. And because that is such a long name, I will frequently abbreviate that by SLE. So SLE means system or systems of linear equations. And this here is an introduction to that topic. We're going to start with an application. And this application is the following. Let me mention first that this is, of course, a very much simplified application, but things like that occur in practice today very often in the context of optimization. And these systems of linear equations are basically the foundation of financial optimization. So what we're doing here is the following. Let's say you are an investment consultant and you have a client that wants to buy certain stocks. Let's say there's 3 stocks the client has in mind and she wants to buy certain amounts of those stocks. Write that down first. So let's say an investment consultant has client who wants to buy certain amounts of 3 stocks, and we call those stocks S1, S2, and S3. More precisely, your client wants to buy 140 shares of S1, 320 shares of S2, and let's say 225 shares of S3. So this is what we call the target portfolio. While you think this is, in general, a good idea, there is one problem here, one challenge that you have to overcome. These stocks could be purchased directly, but let's say they may only be traded at exotic places, maybe abroad, and let's say there are high transaction costs involved with investing in these stocks directly. However, we are able to find another option that is much cheaper. You manage to discover equity funds. Let's say 3 different equity funds. that also happen to invest in these precise 3 stocks. Of course, the number of investments into certain stocks is different for all of these equity funds, but those can be bought locally at a much cheaper price. So the idea that you come up with is, why not buy shares of these equity funds instead? And buy them in a way such that the actual shares that you get mimic that target portfolio you want to have. We'll discuss how this can be done. Let's quickly write down that idea. So, unfortunately, the direct purchase of these stocks incurs high transaction costs. But the consultant is able to find a cheaper option. And that's the following one. There are equity funds, let's call them F1, F2, F3, which are composed of these 3 stocks. And those equity funds can be acquired at a low overhead only. Okay? So you and your client decide you would like to invest in those equity funds instead, but you would still like to reach your target portfolio if that is possible. Now the question, of course, arises, how do you invest in these funds? To answer that question, of course, you have to know how many shares of each stock are contained in one share of each of the equity funds. So let's get that data first. We'll just sum up that in a table. So following table goes. The number of shares of S1, S2, S3 that are contained in one share of F1, F2, and F3 respectively. And again, I am aware that this is a pretty simplified scenario, but it shows you the fundamental ideas. So let's say we have these 3 stocks, S1, S2, S3. We have the equity funds, F1, F2, F3. And now the fund F1 is composed of, one share of F1 is composed of 1 share of S1, 2 shares of S2, and 1 share of S3. For F2, we have 3 shares of S1, 7 shares of S2, 4 shares of S3. And for F3, we get 4 shares of S1, 10 shares of S2, and 9 of S3. If you buy 1 share of, let's say, F2, you get 3 shares of S1, 7 shares of S2, and 4 shares of S3 at the same time. And then remember, we have our target portfolio. And that was, we wanted 140 shares of S1, 320 shares of S2, and 225 shares of S3. So the question is, can that target portfolio be reproduced by buying F1, F2, and or F3? And if so, of course, we also would like to know how many shares of each one should we buy. To answer that question, let's introduce some variables. Specifically, we'll denote the number of shares of F1, F2, F3 that we want to buy by X1, X2, and X3. So let X1, X2, X3 denote the number of shares of F1, F2, F3 that the consultant acquires on behalf of his client. Then the following equations need to hold. So let's have a look at that data here. Again, what we have here is for each fund the number of shares that are included in that fund. Colors here. So we have the red fund F1, the blue fund F2, and the yellow fund F3. Now what we want to do is we want to buy a certain number of F1, F2, and F3 such that we get 140 shares of S1, 320 shares of S2, and 225 shares of S3 simultaneously. So how many shares of S1 do we get if we buy X1 shares of F1, X2 shares of F2, and X3 shares of F3? Well, basically, we have to look at this line here. And we get X1 times 1 shares from buying F1. We get X2 times 3 shares of S1 by buying F2. And we get 4 times X3 shares of S1 through buying F3. So count these numbers here. What we have is 1, 1, 7, 4, yellow numbers, 4, 10, 9. And we get this much shares of S1 by buying F1, this much shares of S1 by buying F2, this much shares of S1 by buying F3. And we want that to be equal to the target portfolio, which is 140. So remember that was S1. For S2, we get 2 times the number of F1 shares that we buy, plus 7 times the number of F2 shares we buy, plus 10 times the number of F3 shares we buy. We want that to be 320. That's our target for S2. And finally, it's 1 times X1 plus 4 times X2 plus 9 times X3 for S3. And we want that to be 200. So this is a system of 3 linear equations here. And the question that we formulated, is there a method to replicate our target portfolio through buying these equity funds? The question is mathematically formulated, is there a solution to this system here, and what does it look like? So that's what we want to know. And before we try to find the actual solution, let's clarify what exactly we mean by a system of linear equations and a solution to a system of linear equations. So let's write down formal definition. What we want to define is what a system of linear equations is. A system of linear equations, or SLE, is specified by the following data. Now, what do we need to specify a system of linear equations? If you look at this one, first thing I would like to know is, of course, the number of equations and the number of variables. Yeah, so that's one basic data point here. Write that down. A number, we usually call this M. Should be a natural number, of course, of equations. And then a number usually called N of variables. In this case, we have 3 equations, M is 3, and 3 variables, so N is also 3. Then we need a right-hand side. These numbers here, the target portfolio in our example, that is the right-hand side of the equations. So for each equation, one right-hand side. A so-called right-hand side, call that beta I M for each equation. And finally, need the equations themselves, and those are characterized by these colored numbers here, right? So those coefficients, those make up the equations. So for each row, each equation, and for each column variable, we need one coefficient. So have here is coefficients. We call those alpha ij. For im, those are the equations, and j in n, those are the variables. So we want that for each variable and each equation. And of course, the coefficient could also be 0. So if a variable doesn't show up in a certain equation, the coefficient would just be 0. Now this equation system, usually written in a certain form, just as we wrote it down above. So what we have is alpha 1, 1 is the coefficient for x1 in equation 1. Alpha 1, 2 is the coefficient for x2 in equation 1, and so on, up to alpha 1 n xn. Right hand side here is beta 1. Then for the next equation we get alpha 2, 1. So the first number is always the equation number, the row. The second number is the variable number here. Column if you want. Alpha 2, 2x2 and so on. Up to alpha 2 and xn, that's beta 2. And this goes on for many, many rows, possibly up to the last one, that is the mth equation, so the mth row in this scheme. Alpha m1 x1, alpha m2 x2 plus, and so on, alpha m n x n, that's equal to beta m. And in this case, we named the variables x1 to xn. You notice the variable names are not really part of our specification. Those are basically just a convention. So you can name them anything you want. The name of the variables doesn't really play a role for the solution. Okay, so these x's, those are called variables. x1, x2, 2xn. Okay, now we know how to write down such a system. Let's talk about what it means for that system to have a solution or to be feasible. Also, pretty straightforward. The system of linear equations is called feasible if there exist values, we call those x1 star, x2 star, and so on up to xn star in R, so those are real numbers. And those need to satisfy all equations at the same time. Satisfy all m equations when substituted for the variables. So if you replace the variables above by these constant values and all equations are satisfied, then that is a solution. And if such a solution exists, the system is called feasible. Okay, so each such n tuple, like 1 star, 2 star, up to xn star, is called a solution of the SLE. And finally, the set of all possible solutions is called the solution space or the feasible region or feasible set. All solutions is called solution space or solution set, or also feasible region or feasible set. And finally, a system of linear equations is called homogeneous if the right-hand side is all 0, if all betas are 0. and inhomogeneous is otherwise. So in our example, we have an inhomogeneous system because the betas are not all 0. The right-hand sides are numbers that are not all 0. This differentiation will be important later on when we characterize solution spaces, because it will be particularly easy to do this for the homogeneous case first. And then from that characterization, derive a characterization for the inhomogeneous case. So NSLE is called homogeneous if beta 1, beta 2, and so on, if all betas are 0. And inhomogeneous otherwise. So if even one of the betas is not 0, the system is inhomogeneous, not homogeneous. Okay, that concludes our introduction into systems of linear equations. So the notation. In the upcoming videos, we'll be concerned with the solution of these systems, and then we can see if our investment consultant will be able to find a solution to his problem here. I'll see you then.